Moving 20 tons of soil with a precision of 20 millimeters requires more than operator intuition. This level of accuracy is driven by real-time kinematic positioning. By comparing satellite carrier phase measurements from a roving antenna to a fixed base station, the system eliminates ionospheric delay errors. The resulting three-dimensional coordinate allows the machine to know its exact location on the planet within the width of a human finger. This positioning data flows into an onboard computer that compares the current blade edge position to a digital design surface. Instead of relying on physical stakes and manual string lines, the machine uses a virtual map to determine whether to cut or fill. This synchronization between orbital satellites and hydraulic cylinders transforms heavy machinery into a surgical tool for site preparation, ensuring that the physical foundation of any building matches its mathematical blueprint. To achieve centimeter-level precision, a local base station must provide differential corrections to the machine. While standard satellite signals provide a position within several meters, the base station remains at a known, static coordinate to calculate the exact atmospheric interference at that moment. It broadcasts these corrections via radio or cellular internet to the roving machine. The machine receiver then subtracts the error from its own satellite data. This process happens at least 10 times per second, ensuring the blade position is updated in real time. Without this constant data link, signal drift would render automated grading impossible for civil engineering tolerances. The reliability of this link depends on line of sight or robust network coverage, forming the backbone of any automated construction site. This spatial reference frame ensures that every pass of the dozer aligns perfectly with the intended architectural grade.
In environments where satellite signals are obstructed by tall buildings or dense tree cover, robotic total stations provide a local positioning system. These instruments use a motorized tracking head to follow a glass prism mounted on the machine. By measuring the precise horizontal angle, vertical angle, and slope distance using a phase shift or time of flight laser, the total station determines coordinates with millimeter accuracy. This is significantly more precise than satellite positioning, making it the preferred choice for final subgrade finishing and concrete paving. The system maintains a high-speed data connection to the machine, transmitting the coordinate updates instantly. If the line of sight is broken, the tracking head enters a search pattern to reacquire the prism. This optical method removes the vulnerabilities of orbital signal interference, providing a high-fidelity alternative for tight-tolerance infrastructure projects where satellite coverage is compromised. While satellite systems excel at horizontal positioning, vertical accuracy often requires a rotating laser for millimeter precision. A laser transmitter sits on a tripod and projects a level or sloped plane of light across the entire job site. A vertical receiver on the machine mast detects this beam. By integrating this light reference with the satellite data, the control system achieves superior height control. This is vital for drainage systems where a fraction of a percent in slope determines the success of water runoff. The rotating laser operates at high frequencies, providing a constant elevation reference that compensates for the vertical noise inherent in satellite signals. This hybrid approach combines the global flexibility of satellites with the local stability of light. Engineers use this setup for building pads and parking lots, where water ponding must be strictly avoided through perfect plane management across large surface areas.
The intelligence of the machine resides in the digital terrain model, a three-dimensional representation of the final design. Engineers convert computer-aided design files into specialized formats that the machine control computer can process. This model contains every break line, slope, and elevation point of the project. As the machine moves, the software calculates the shortest distance between the current blade position and the nearest point on the digital surface. It then displays a cut or fill value to the operator or sends a direct command to the hydraulics. This eliminates the need for manual grade checking and stake resetting, which often cause delays and human error. The model also allows for real-time volume calculations, letting project managers track exactly how much material has been moved. This data-driven approach ensures that the physical reality of the site matches the digital intent of the designer. Accurate grading requires more than just knowing where the machine is. The system must also know the orientation of the blade. Inertial measurement units containing gyroscopes and accelerometers measure the pitch, roll, and yaw of the machine and its attachments. These sensors operate at hundreds of cycles per second to detect sudden movements or vibrations. By combining this inertial data with positioning coordinates, the system calculates the exact position of the blade tips even when the machine is tilting on a steep slope. This sensor fusion is communicated through a controller area network bus, which acts as the nervous system of the machine. It allows multiple components to share data with minimal latency. This high-speed communication ensures that the control system can react to changes in terrain faster than a human operator could perceive them, maintaining a smooth grade over uneven or loose ground.
The final link in the automation chain is the hydraulic interface. The control computer sends electrical signals to proportional solenoid valves that regulate the flow of hydraulic fluid to the lift cylinders. Unlike standard on or off valves, proportional valves allow for fine adjustments, moving the blade just a few millimeters at a time. This results in a smooth finish rather than a stepped or jagged surface. The system often employs a closed-loop feedback mechanism, where sensors on the cylinders report the actual position back to the computer to confirm the command was executed correctly. This automation reduces operator fatigue and allows less experienced drivers to achieve professional results. By taking direct control of the main lift and tilt functions, the system ensures that the physical work is performed with the same precision as the digital calculation, regardless of the resistance provided by the soil. Effective grading depends on understanding the physics of soil mechanics and material displacement. When a bulldozer blade cuts into the earth, it creates a rolling wave of material that provides resistance. The automated system must balance the desired grade with the available engine power and traction. Advanced controllers adjust the blade height to prevent track slip while maintaining the maximum possible load. This optimization improves fuel efficiency and reduces wear on the undercarriage. The system also accounts for the bulk factor of the soil, which is the increase in volume after the earth is excavated. By maintaining a consistent blade load through automated adjustments, the machine ensures uniform lift thickness. This uniformity is essential for subsequent compaction, as uneven layers lead to structural failures or sinkholes in the finished infrastructure. Automation ensures that every layer of the earthwork is geometrically consistent.
Paving automation extends these principles to the application of asphalt and concrete. On an asphalt paver, the system controls the toe point cylinders to adjust the screed height and angle of attack. This determines the thickness and smoothness of the mat. Modern pavers use non-contact sonic sensors to average the surface of the existing grade, removing local bumps and dips. Additionally, thermal mapping systems monitor the temperature of the asphalt mix in real time. Since asphalt density depends on temperature during compaction, this data is critical for the structural integrity of the road. The system can also integrate with material delivery trucks to ensure a continuous flow, preventing the screed from stopping and creating a bump. This level of control ensures that the final driving surface meets strict International Roughness Index standards for high-speed highways and critical infrastructure projects. The final stage of the process is real-time verification and as-built documentation. As the machine completes its final pass, the control system logs the actual coordinates of the finished surface. This data creates a digital twin of the constructed site, which can be compared directly to the original design to verify tolerances. Any deviations are flagged immediately, allowing for corrections before the equipment leaves the site. This continuous quality control loop reduces the need for traditional surveying after the work is done. The digital record provides a permanent history of the project, which is invaluable for future maintenance or expansion. By closing the gap between design, execution, and verification, automated machine control maximizes efficiency and ensures that complex civil engineering projects are delivered with mathematical certainty. The result is a more durable and accurately constructed environment.